What if I told you the greatest threat to a $4.3 million M1 Abrams is not a Russian anti-tank guided missile, but its own idle revolutions per minute? Let us initiate a full three-dimensional cross-section cut along the longitudinal axis of this 68-ton beast. We will strip away the outer layers of the highly classified depleted uranium mesh and the composite Chobham armor plates. What remains exposed in the rear engine compartment is not a conventional diesel block, but a weaponized aerospace propulsion system, the Honeywell AGT1500 gas turbine. Look closely at this compact metallic core. You are staring at a machine that generates 1,500 shaft horsepower. Yet it possesses a thermodynamic paradox so severe that it single-handedly transformed the United States Army $38 billion modernization program into a logistical nightmare in the Arabian desert. To understand why this marvel of engineering became a tactical liability, we must dive directly into the fluid dynamics of its combustion cycle. Let us isolate the engine block and make the casing transparent. Unlike a traditional reciprocating piston engine that scales its fuel consumption dynamically with the vehicle speed, a gas turbine operates on a continuous combustion loop. Watch the dual-spool compressor section spinning violently. The forward low-pressure compressor pulls in atmospheric air, forcing it through multiple titanium alloy blade stages, compressing it to maximum density before slamming it into the high-pressure compressor. These blades are rotating at a staggering 30,000 revolutions per minute. To put that extreme mechanical violence into perspective, that is 500 full rotations every single second, creating a localized pressure differential strong enough to suck in a human body instantly. This continuous high-velocity airflow is then injected into the combustion chamber, where it mixes with aviation-grade jet fuel and ignites into a continuous vortex of flame, reaching temperatures exceeding 3,000 degrees Fahrenheit. That is hot enough to melt standard structural steel into a glowing puddle within seconds. But here's the fatal mechanical flaw. This turbine requires a colossal, uninterrupted volume of compressed air to maintain the critical pressure ratio inside the combustion chamber, regardless of whether the tank is charging at 45 miles per hour across the sand or sitting completely stationary. Look at the idle RPM metrics on our diagnostic overlay. Even when the M1 Abrams is not moving a single millimeter on the ground, the high-pressure compressor must still spin at over 20,000 revolutions per minute just to keep the internal flame from extinguishing. This rigid physical requirement leads to the ultimate static consumption trap. The engine must devour 10 gallons, or nearly 38 liters, of aviation fuel every single hour just to stand still. Imagine dumping a large jerry can of highly refined kerosene onto the ground every 60 minutes, purely to keep a parked machine breathing. Why not simply shut the engine down when the tank is in a static defensive hull down position? Let us analyze the restart sequence. If the crew powers down the AGT1500, restarting it requires a massive electrical surge from the battery banks to spool the heavy turbine blades back up to minimum operating RPM, a process that takes critical seconds. In modern armored warfare, taking 30 seconds to ignite your engine and move out of the path of an incoming laser-guided artillery shell is a guaranteed death sentence. Therefore, standard operational doctrine dictates that the turbine remains running, burning through the massive 504-gallon internal fuel cells at a terrifying rate. During the 1979 procurement phase, military engineers were mesmerized by the extreme acceleration curve and the multi-fuel capability of the turbine design. It could technically burn diesel, marine gas oil, jet fuel, or even pure alcohol in a theoretical emergency. However, this $38 billion acquisition blinded the brass to a brutal physical reality. They successfully mounted a jet engine inside a heavily armored steel box, but they completely failed to account for the catastrophic fuel logistics required to keep it fed in a hostile environment with zero established supply lines. Let us look deeper into the Recuperator, the massive cylindrical component dominating the rear exhaust section of the engine. Make the outer shell of the Recuperator transparent so we can trace the thermodynamic airflow. The Recuperator is essentially a massive heat exchanger, constructed from layers of incredibly thin Inconel superalloy, a material specifically engineered to maintain structural integrity under extreme thermal stress. The exhaust gases, leaving the turbine at over 1,000 degrees Fahrenheit, are routed through this matrix of microscopic channels. Simultaneously, the freshly compressed cold air from the intake is forced through adjacent channels. The thermal energy transfers across the thin Inconel walls, preheating the incoming air. However, let us simulate the actual desert battlefield conditions. The Abrams requires a massive volume of air, drawing in over 300 cubic feet of atmosphere every single second. In the desert, this air is saturated with microparticulate silica dust. The silica bypasses the filters and is pulled directly into the spinning compressor stages. The silica hits the combustion chamber, where the 3,000 degree Fahrenheit operating temperature instantly melts the sand into liquid glass. This molten glass then flows into the microscopic channels of the Recuperator, cooling and solidifying instantly. Watch as our fluid dynamics simulation shows the internal pressure spiking. As the airflow is restricted, the engine temperature skyrockets, and the electronic control unit desperately injects even more raw fuel into the combustion chamber to compensate for the lost pressure. The fuel efficiency plummets further, amplifying the static consumption trap and worsening the $38 billion logistical crisis. Let us rotate our three-dimensional model 180 degrees to analyze the rear exhaust grille. The thermodynamic byproduct of generating 1,500 shaft horsepower is an unrelenting exhaust plume radiating at over 1,000 degrees Fahrenheit, or 537 degrees Celsius. To understand the physical magnitude of this thermal emission, imagine standing behind a commercial jet engine during takeoff, but concentrated into a rectangular armored vent. This extreme heat output creates a severe tactical limitation. Standard combined arms doctrine relies on infantry squads advancing behind the physical bulk of the main battle tank for cover against small arms fire and shrapnel. However, the Abrams exhaust acts as an invisible wall of thermal radiation. Any infantryman attempting to take cover immediately behind the idling engine will suffer severe first-degree burns to exposed skin and risk melting their synthetic tactical gear within seconds. Furthermore, switch our visual overlay to the infrared spectrum. Watch the digital thermal bloom expand across the screen in vivid shades of white and red. While the Chabum composite armor successfully deflects kinetic energy penetrators from the front, the engine exhaust turns the rear quadrant of the tank into a blindingly bright beacon on enemy thermal imaging systems. From 3 miles away, a Russian anti-tank guided missile crew does not need to see the desert camouflage paint. They simply lock their optics onto the massive thermal anomaly radiating against the cold ambient background. To mitigate this blinding infrared beacon, engineers attempted to install a rear exhaust deflector, a heavy steel louver designed to angle the thermal blast upwards and dissipate the heat plume. Let us render this deflector in wireframe mode. While it marginally reduces the immediate danger to trailing infantry by directing the 1,000-degree airflow away from the dirt, it inadvertently creates a massive vertical thermal column. Enemy reconnaissance drones flying at high altitudes can detect this rising column of hot air from dozens of miles away, completely nullifying any attempt at operational stealth in the cold desert night. The laws of physics dictate that energy cannot be destroyed, only transferred, and the Abrams transfers its excess energy in the most conspicuous manner possible. To fully grasp the magnitude of this engineering miscalculation, we must compare it side by side with its European counterpart. Let us render a holographic projection of the German Leopard 2 main battle tank right next to our Abrams. Strip away the Leopard hull armor to reveal its beating heart, the MTU-MB-87-3V12 twin-turbo diesel engine. When we initiate a synchronized combat performance simulation, the stark mechanical contrast becomes undeniable. The German V12 block utilizes traditional reciprocating pistons. When the Leopard 2 sits in a static ambush position, the driver drops the engine to idle, and the mechanical fuel injectors scale back their output to a mere trickle, just enough to keep the heavy steel crankshaft rotating at a few hundred revolutions per minute. The Leopard can maintain this defensive static posture for over 24 hours on a single tank of diesel. Conversely, our Abrams, locked in its continuous turbine combustion cycle, burns through its internal reserves 4 times faster in the exact same static scenario. The American turbine traded long-term operational endurance for instantaneous acceleration, a tactical decision that looks brilliant on a testing ground, but becomes a fatal liability in a protracted theater of war. Before the power of the turbine reaches the drive sprockets, it must pass through the Allison X 1100 3B hydrokinetic automatic transmission. Let us isolate this massive gearbox and make the outer casing transparent. The turbine output shaft spins at 30,000 revolutions per minute, but the transmission must step this incredible rotational velocity down through a highly complex planetary gear system to generate usable low-end torque for the 68-ton chassis. Watch the internal hydraulic clutches engage and disengage under thousands of pounds of pressure per square inch. This hydrokinetic system provides seamless, uninterrupted acceleration, but it also siphons off a significant percentage of mechanical efficiency through parasitic heat loss. The transmission fluid alone requires a massive dedicated oil cooler mounted directly above the turbine exhaust, adding another critical layer of thermal vulnerability to the rear engine deck. Now let us zoom out from the individual tank anatomy and render a macro-scale, tactical holographic map of an armored brigade combat team advancing across the Iraqi desert. We will represent the Abrams tanks as heavily armored spearheads pushing deep into hostile territory. But look closely at the fragile logistical tether trailing behind them. Because the Abrams operates with an effective combat range of only 265 miles, or barely 8 hours of continuous tactical maneuvering, it cannot survive independently. It is absolutely physically bound to the heavy, expanded mobility tactical truck, or HEMTT, an unarmored, 8-wheeled logistics vehicle carrying 2,500 gallons of highly flammable aviation fuel. We are highlighting the HEMTT supply convoy in stark red on our map. Let us simulate the actual combat refueling procedure known as refuel on the move. This is not a casual pit stop. Under the constant threat of enemy artillery fire, a platoon of Abrams tanks must align with a forward-deployed fuel blivet. The turbine engine requires immense volume, meaning the high-pressure hoses must pump over 100 gallons per minute into the armored fuel cells. During these critical 10 to 15 minutes, the entire armored formation is completely stationary, clustered together, and highly volatile. A single shrapnel fragment striking the pressurized fuel lines would ignite a localized firestorm, instantly vaporizing the logistics crew and permanently crippling the armored advance. If an enemy force wants to neutralize a 68-ton Abrams, they do not need to penetrate the depleted uranium armor mesh with advanced weaponry. They simply need to fire a basic rocket-propelled grenade into the thin aluminum hull of the trailing fuel truck. By severing the logistical artery, the mighty turbine is starved of its critical fuel supply. Within hours, the internal pressure drops, the combustion chamber goes cold, and the $38 billion apex predator of the battlefield is instantly reduced to a massive, immobile steel bunker, completely useless for maneuver warfare. This is the ultimate mechanical paradox of the late 20th century. United States military engineers succeeded in creating an armored vehicle capable of dominating any opponent in a direct kinetic engagement. Yet they simultaneously engineered its greatest vulnerability by ignoring the fundamental laws of thermodynamics and fluid dynamics. A machine built to crush everything in its path ultimately found itself chained to a relentless logistics fuel pump. If you want to continue dissecting the mechanical truths hidden beneath the armor of history's most terrifying war machines, hit the subscribe button for DEFUNCT. Leave a comment below suggesting which piece of military hardware we should tear down to its molecular components in the next video.